So today we cover section 11.1, sequences. So this is the last stretch of this class. We have pretty much finished integration and all the related techniques. Now we have a very different topic. But there will be connections between sequences and series and integration, as will become apparent. But today we just talk about basic notions and definitions. Very easy chapter. So a sequence is nothing but a list of numbers written in a certain order. So we can say A1, A2, AN, ... So in this class, we'll be dealing with infinite sequences. So it's an infinite number of terms. So this is called the first term. This is the second term. And this is the nth term. Okay, these are the words that we'll be using a lot. There are three ways to denote a sequence. Okay, so this is notation number one. Notation number two is like this. AN. So this means that we have a bunch of numbers. And they are called A1, A2, and so on, right? So this is a shorthand notation. And notation number three is this. AN, where n changes from 1 to infinity. So the subscript tells you where n starts, usually at 1, sometimes at 0. And it goes all the way up to infinity. So for example, so let's consider the following sequence: 1/2, 2/3, 3/4, 4/5, ... Okay, so let's figure out how this can be written as one formula. So as you look at this, you can discern a pattern. What's the pattern? When n equals 1, the numerator is 1, and the denominator is 2. When n equals 2, the numerator is 2, and the denominator is 3. When n equals 3, you can see that the numerator is always given by n, and the denominator is that plus 1. So this is the same as to say that it's n divided by n plus 1, where n goes from 1 to infinity. Or we can say that an is given by n plus 1, right? So by looking at this pattern, by looking at the first few terms of the sequence, we were able to get a pattern. And we're able to come up with this expression, which tells you the general term. Now I can say what is A100 is. That will be 100 divided by 101. How about this one? 0, 1, square root of 2, square root of 3, square root of 4, like this. Okay, so you can see that there is a pattern here too, because even though it looks like the square roots start from the third one, really we can put them here too, right? These are all square roots. So we can say that an is going to be a square root of something. Of what? So when n equals 1, we have a square root of 0. N equals 2, we have a square root of 1. So what is the square root of for a general n? N minus 1. Okay, so we can say that this is square root of n minus 1 from 1 to infinity. Okay? So we're going from particular to general. Another example that is useful is like this. So okay, so let's find a general term here. It's more complicated. First thing that you notice is that the sign alternates of plus, minus, plus, minus, plus, minus. So every time we see something like this, there's a trick to do it. So we have to say that an is going to be a multiple of -1 to a certain power. So actually, let me start like this. So consider -1 to the power of n. What is the sequence? So when n is 0, well, I'm sorry, when n is 1, we get -1. N is 2, we get 1. N is 3, we get -1. So this is a little device that makes alternating signs, plus, -1, plus, minus, and so on. But written like this, the first term is has a minus sign, right? So how can I make the first term positive? I multiply by -1, or you can say like this, right? So in this case, when n equals 1, I have -1 squared, so that's +1. N equals 2, I get -1. N equals 3, +1, and so on. So this gives me the right sign, okay? I have more stuff going on. So the easier part is the numerator. I think it goes 3, 4, 5, 6, 7. So when n equals 1, we get 3, so it's n plus 2. You can see that, right? N plus 2. And in the denominator, what do you see? 5, 25. These are powers of 5. So this is the first power. So when n equals 1, we have the first power of 5. This is the second, and so on. So it's 5 to the n. So this is my general term, an, for this particular case. See, step by step, we were able to reconstruct the whole pattern. Okay, question? Now, there are several famous sequences. Okay, so something that I want to tell you is the Fibonacci sequence. So Fibonacci was an Italian mathematician who became interested in the reproduction of rabbits and how quickly they reproduce and their numbers increase. So he came up with the following sequence. So let's suppose that f1 is 1, okay, and f2 is 1. And then we define fn is defined recursively to be given by fn minus 1 plus fn minus 2. What does it mean? To create fn, we take the previous two and add them together. So what does it mean? I know f1 and f2, they're given. What's f3? We have to take f1 plus f2. 1 plus 1 is 2. f4, I have to add f2 plus f3. And by the way, before all the sequences, I denoted as an. This is fn, right? But it doesn't matter. It's just a notation. F for Fibonacci, famous guy. So I have to add f2 and f3. So f2 is 1 and f3 is 2. So I have 1 plus 2 is 3. Next, f5 is f3 plus f4. f3 is 2. And the next one is 3 is 5. Okay, let me do one more. f6 is f4 plus f5 is 3 plus 5 is 8, etc. Okay, so rabbits, it has very little to do with rabbits, it turns out, but it describes many other beautiful things in nature. For instance, if you look at a pineapple or a sunflower, you can see certain spiral structures as the seeds are formed. And I cannot draw it, I didn't draw it well. There are several spirals that emanate from the middle, like this. So this is like looking at the sunflower or onto a pine cone from the top, right? So it turns out that these spirals are described by using Fibonacci sequences. And there are many scientists who are trying to explain this universal pattern in nature. Why does nature like this sequence so much? And there are many interesting explanations of that. Okay, and so here we can very easily figure out what the next term is. So here we need a little bit more work because we have to know the previous terms. Here we don't need any work. We just substitute the number n and we calculate the term. So this is given by just one function. In other sequences, we don't have an easy way to determine the next term. I'll give you one example of such a sequence. So number of students enrolled in math 2B in year n is given by an. Okay, so this is a sequence whose numbers are unpredictable. Okay, but we don't have a formula for this. But nonetheless, we have a sequence associated with this. How do we plot sequences? So let me show you. So presenting sequences. So how do we present a function? We usually plot it, right? F of x, we plot it as a function of x. With sequences, we can do the same thing. So one way of doing it is a graph. So for example, let's suppose that an is given by n over n plus 1. I think this is our first example. Yes, this one. Okay. So how can we view this? We just simply set n to be our horizontal axis. And so we only have discrete values. 1, 2, 3, 4, and so on. The first number is 1/2. Then we have 3/4. No, 2/3. Then we have 3/4. And so on. Like this. And we can even connect it, right? Although the lines connecting the dots don't mean anything, really. It's only the points that count. So this is a kind of a discrete function. And so this is the first way of representing this sequence. The second way is called the number line. So let's suppose that this is 0 and this is 1. Okay, and I'm going to put a point on this line that corresponds to each consecutive term. So the first term is 1/2. The next term is 2/3. The next one is 3/4. Then I have 4/5. And I continue to put these points. And I can see that they become denser and denser, closer and closer together. For this particular example. You can also see that here we don't have a constant slope. It becomes flatter and flatter, this line. Somehow we feel that this thing may have a horizontal asymptote. Okay, it may have a limit. So, indeed it does. Let's define a limit of a sequence. So we can talk about a limit L of a sequence So formally speaking, a sequence an has the limit L, and we write, so this is notation, it must look familiar, limit as n goes to infinity of an is L, or we can also write an goes to L as n goes to infinity. Okay, so this happens if for any epsilon greater than 0, there is a number n, integer, such that if n is greater than n, then an minus L is less than epsilon. Okay, so something has a limit. It means that it gets to this number L arbitrarily close. Okay, and it never leaves the vicinity. Once it's there, it's going to stay there. So let's suppose that my limit is L. Let me measure like 1% error. Let's suppose that I want to reach L within the precision of 1%. The fact that the sequence has a limit L means that I can find a number n, for instance 1 million, such that after this number, all the an's are going to be within that precision of the number L. Okay, so this is exactly the same definition as you remember for functions. So this epsilon works like a trap. Let's suppose that this is L, and my sequence starts somewhere far away. So A1, A2, and then I go A3. Could be anywhere. But let's suppose that I know that it has a limit. It means that for arbitrary epsilon, I can put a bracket like this. So this length is epsilon. This length is epsilon. And this, eventually, starting from a certain number n, the sequence is going to be trapped within this trap and never escape. So as the sequence jumps up and down, or doesn't, at some point it's going to enter this interval, and it's going to remain there forever, starting from that number n. Okay? And then I can make the trap smaller. I can make it very small, like this. So this is epsilon. So it's going to take a long time until it gets there, but eventually it will. Maybe it will take 1,000,000 iterations until you're inside, but once you're there, you stay inside. So this is the explanation of this definition. How do we, in practice, find out whether a sequence has a limit? So let's find the limit as n goes to infinity of this sequence. Okay. Do you have any questions? Questions? Okay. So in this case, we can perform the following manipulations. We can say that n plus 1 is the same as n plus 1 minus 1. Remember, we did this with integrals sometimes. We add and subtract the same number, and it remains the same. And now we can write this as 1 minus this. Okay. So the limit of this is the same as the limit of 1, this. And what is the limit of this sequence as n goes to infinity? 0. As n goes of this. the limit of this, the limit of the whole thing, you're right, is 1, uno. The limit of this is, of course, 0, right? As n increases indefinitely, this goes to 0, right? So we can say that the limit is equal to 1. Okay. So not all sequences have limits. Question?
For that limit, you can use L'Hopital's too, right? Because it's an indefinite form.
Yes, you can. Except, so this is one of those cases when you don't really need L'Hopital. And so let's consider a function. So very often, if the sequence is given like this analytically, if we have a general formula, we can use functions. Okay, let's suppose that the function f is given by this, right? And then we can find the limit of the function. And if we know the limit of the function, it's going to be the same as the limit of the sequence. So how would we find the limit as x goes to infinity of this function? One could apply L'Hopital, but the easier trick that we usually learn is the following. We divide the numerator and denominator by x, right? So we have 1. And now we notice that 1 over x goes to 0, and it's 1. Okay? So in this case, L'Hopital is not necessary, but there will be other examples, I think today, where we can use L'Hopital. And L'Hopital rule only applies to functions of a continuous variable. But we can always translate our results for the function to sequences. We can actually write it as a theorem. Okay? Suppose we know suppose that an is given by some function f of n. Okay? Then, if the limit as x goes to infinity of f of x is equal to L, then the limit as n goes to infinity of an is the same thing. Okay. So this is exactly what I just did. I looked at an, I expressed it as a function of a continuous variable x, calculated the limit, and the limit is the same for the sequence as it is for the corresponding function. Okay? So this is something that allows us to apply calculus to sequences, as long as we know the formula for an. Okay, I'll show you some examples where we don't have a formula for an. Oh, in fact, we already had an example. Remember Fibonacci sequence? There is no functional form there. That sequence is not given by a function. It's given sequentially. Okay, so this theorem would not be useful in this case, in the case of Fibonacci sequence. One more statement with regards to limits. Some sequences increase indefinitely. So, definition. So, if we say that the limit as n goes to infinity of an is equal to infinity, this means that for any m, there is a number n such that if n is greater than n, an is greater than m. So let me show you an example. Consider the sequence with an given by n squared. What is the limit as n goes to infinity of an? What do you think? What happens to n squared as n goes to infinity? It also goes to infinity. What does it mean? If I plot it, it goes like this. It kind of outlines a parabola, point by point. Okay? And if I want to set a limit, like let me choose a really big number, m, 5 million. Okay? There is going to be a number n, starting from which we're bigger than this. Let me take 10 million. This is another m capital. Then starting from here, we're going to be even bigger. And no matter where I put the upper limit, it's going to exceed it, starting from a certain number n. So this is what this definition says. Okay, questions? Okay. So there are several results that apply to limits of sequences just as they do to the limits of functions. So if an and bn are convergent, so what does it mean, convergent? Convergent means that they have a finite limit. Have a finite limit. Okay? Then we can talk about the limit as n goes to infinity of their sum. So the limit of the sum is the sum of the limits. Okay. We can talk about the limit of a number times a sequence. So take a sequence that has a limit. Multiply each term of that sequence by 5. What's going to be the limit of the new sequence? It's the old limit times c. So it's c times the limit of an. And let me put etc. here to save time. You have a similar theorem about a product of two sequences. You have a similar result for the ratio, the difference, and the power. Okay, so and it's all the same as we had for functions. Okay, no difference. The squeeze theorem. What's the squeeze theorem? So in Russian, this theorem is called the theorem about two policemen. Do you know that? So that's what they taught me. Like, so let's suppose that we have a sequence that we don't know the behavior of, and we have two policemen. One is approaching on this side from below, okay, and the other one is approaching from above, and they both go to the same place, right? So the criminal cannot escape. It has nowhere to go. So if the limit of an and the limit of bn, so these are the two policemen, A and B, is equal to L, and A and Bn surround Cn. This is the criminal. C is for criminal. I'm just making it up. So one is always bigger and the other one is always smaller. Then the criminal has no place to go except L. Okay? So if we have two sequences whose limit we know, and they're on the two sides of the unknown sequence, we can conclude about the limiting behavior of that sequence. Okay? And another simple theorem is if we know that the limit of the absolute value is 0, then the limit of the sequence itself is also 0. So if the absolute value of a certain sequence tends to 0, then the sequence with changing signs will have the same behavior. Okay. So I want to consider some examples of different types of behavior. So I start very simple, okay? Suppose an is equal to 5. Does an converge? Yes, because it's a very boring sequence. It goes like this. This is 5. And the limit, as n goes to infinity of an, is 5. That's completely obvious. Okay? Next, let's suppose that an is given by -1 to the n. Does an converge? Okay? What's the answer? No, because it behaves like this. The first term is negative, -1, and then it's positive, negative, positive, like this. And it keeps oscillating. It never approaches any particular number. It keeps jumping. Okay? So no. Okay. And you can prove it by using the n epsilon definition. That's really easy. What's next? Next example. So let's look at the same question. Does it converge? N square root of 1 plus n. Does this converge? Okay. So how do I approach this? This is easy because my sequence is given by a function of n. Okay, so we consider the relevant function, which looks like this. So we have x over 1 plus x. Okay, and we have to calculate the limit as x goes to infinity of f of x. If this converges to a certain limit, then so does the sequence. So we have x over square root of 1 plus x. So we can divide everything by x, numerator and denominator, right? So we have 1 over x squared plus 1 over x. What happens to this? So x goes to infinity. What happens to the denominator? 0. What happens to this sequence if its denominator goes to 0? It goes to infinity, right? So the denominator becomes vanishingly small as x becomes large. So the whole thing actually blows up. Therefore, the limit as n goes to infinity of this guy is also infinity. So we use the knowledge of the corresponding function and its limit to conclude stuff about the sequence. Oh, here's L'Hopital. Okay, you asked me for L'Hopital. I'll give you L'Hopital. So how about an is given by log n over n. So we consider f of x, which is log x over x. What is the limit as x goes to infinity of log x over x, right? So now it's not a bunch of powers, and dividing through by x obviously won't help, so we use L'Hopital. We can say that this is infinity over infinity, so we take the derivative of numerator and denominator. So I have 1 over x, so the limit is equal to 0. Okay? Therefore, the limit as n goes to infinity of log n over n is also 0. Questions? Okay. So remember this little theorem here. Let's apply this one. So let's suppose that an is minus 1 to the n over n squared. Okay? What is the limit of this? This theorem tells me that if I know something about the absolute value of the sequence, then, and if it goes to 0, then so does the sequence itself. So consider the limit as n goes to infinity of the absolute values. Okay? This way I can ignore the minus 1 to the n. So this is the limit of simply 1 over n squared. Okay. So this is easy, right? As n goes to infinity, 1 over n squared goes to 0. And then I apply theorem. And I conclude that the limit of the actual sequence is also 0. Questions? Question?
Wouldn't the limit as n goes to infinity of 1 over n squared be infinity?
So n goes to infinity. So we can think of it as, for instance, 1, 10, 100, 1,000, right? So what happens here? Right? Yeah. So it goes the other way. N grows, 1 over n squared decays. Very good. Oh, and there are some general results that apply to this kind of sequence. So consider the sequence an given by 1 over over n to the power p. When does this converge? Right? So this is the question that I want to ask. Let's just look at the notation. Am I using the right notation? I don't know. So if p equals 0, then we can say that an is equal to 1 converges. If p is equal to minus 1, an is 1 over n to the minus 1, so it's n. It diverges. If p is equal to plus 1, an is 1 over n, converges. So somehow we can see that depending on the sign of p, this sequence behaves differently. Okay? One can show that if p is greater or equal to 0, an converges. So this example that we just looked at involved 1 over n squared. This corresponds to p equals 2. Okay. The next definition is that of a sequence bounded above and below. if there is a number m such that an is less or equal to m for all n, then we can say that an is bounded from above. This definition says that there is a roof such that this sequence doesn't pass through the roof. It never becomes greater than n. We can limit the sequence by this roof, by this large number, such that it never exceeds it. And if there is a number m such that am is greater or equal than m for all n, then we can say that an is bounded from below. Okay. For example, so let's suppose that an is n squared. Is this bounded from above? No, it keeps increasing. Is it bounded from below? Yes, by what? 0 or 1 or minus 35 or any of these numbers, right? So it's bounded from below. For example, by m equals 0, not bounded from above. Okay? A few more definitions. If a sequence satisfies an plus 1 is greater or equal than an, then sequence an is increasing. If a sequence satisfies an plus 1 is less than an, then an is decreasing. Okay? For example, look at the sequence 3 divided by n plus 5. Okay? I want to show that this is a decreasing sequence. How do we show this? So an is given by 3 over n plus 5. And an plus 1 is given by 3 divided by n plus 1 plus 5. So it's 3 over n plus 6. Therefore, I can say that an is 3 over n plus 5 is less than 3 over n plus 6, which is an plus 1. So an is less than an plus 1. I got it wrong, right? It's greater. Sorry. So it's decreasing. How else can you show that this is a decreasing sequence? You can see that this is a simple function. F of x is 3 over x plus 5. And you can show that the function is decreasing by calculating its derivative. You can see that for any value of x, the derivative of this function is negative. So the function decreases. Therefore, the sequence decreases. So there are two ways to show that this sequence is decreasing. Two more definitions. No, one more definition. sequence that is increasing or decreasing is called monotonic. Okay, and related to this, there's an important theorem which I wanted to give you. It's called the monotonic sequence theorem. And it's very simple. Every bounded monotonic sequence is convergent. Okay. So let me show you some examples really quickly. So let's suppose that an is given by minus 1 to the n. I want to ask you, is it monotonic and is it bounded? So for sure this guy is bounded. Plus 1, minus 1, plus 1, minus 1. So it's bounded by minus 2 or plus 2. So it's bounded. Is it monotonic? Is it decreasing or increasing? Neither. Not monotonic. Does it have a limit? No, we already established that it jumps around, doesn't have a limit. Okay, no limit. Okay. How about this one? N cubed. Is it bounded? No, it's not bounded from above. Not bounded from above. Above. Is it monotonic? Yes. Increases monotonically, so monotonic. Does it have a limit? No, no limit. So to these two, the theorem actually doesn't apply. The last example is when it does apply. So let's consider an given by n plus 1. Okay? So you can say that all the values an for sure are greater than 0, but they're also smaller than 1, right? Because we divide by something that is greater than the numerator. So this guy is bounded. Okay. Is it monotonic? So we can take the derivative of the corresponding function, or we can plot it. We already plotted it. It looks like this. So we say yes. Therefore, theorem applies. It has a limit. And in fact, we know that L equals 1. Question?
Yeah. So basically, all of the monotonic sequences that have a limit are in that kind of format, right? Fraction.
Not necessarily. No. They don't have to be a fraction.
Which other one? What's the example one?
We'll have many examples. So for instance, an is e to the minus n squared. That's okay. Thank you.